Hey guys, let's solve decode ways. So the problem statement is that we have intercepted a secret message encoded as a string of numbers, and the message is decoded via the following mapping, which is that for each of the 26 letters, it gets a mapping from 1 to 26. So pretty standard. And basically, we're trying to find the number of potential messages that the intercepted secret can represent. So as an illustration of the example, 226 can be broken down into 2 and 26, or 22 and 6, or 2 and 2 and 6, each of which gives a unique message. Hence, this should give 3, because 226 can represent 3 potential messages. So how do we formalize how to solve this problem? Well, this is a DP problem, and DP is all about breaking down a complicated problem into simpler problems, all the way until we break the problem down into the simplest base case and build up from the base case. So how do we do this? Well, to illustrate the full problem, let's consider the number 1202. If we have 1202, and let's say we pass it into the function w, the function w should take this number and return the number of total possible encodings that the number given can represent. So how do we calculate 1202? Well, from a top-down approach, what choices do we have? We can start from the very last digit. If we were to start at the very last digit, how many choices do we have? Well, we can decode the last digit by itself, or we can decode the 2 digits, with the last digit being the last of the 2 digits, right? So we can decode a single digit or 2 digits, because in our mappings, we either have single digit numbers or double digit numbers, like 13. So we can either decode 2 or decode 02. If we decoded 2, that becomes how many ways can we decode 120, right? And if we decoded the last 2 digits, 02, then the problem becomes how many ways are there to decode 12? And the sum of number of ways to do both options is going to give us the total number of mappings for 1202, right? And this is where we have to consider valid mappings. 02 in the example is not a valid mapping because only 2 is mapped to B, not 02. 02 doesn't map to anything. So what this means is that if the 2-digit number that we are trying to decode is not a valid 2-digit number, then we don't even have to consider this branch, right? There's nothing to add here, because we cannot possibly decode the 2 digits. We can only, if we start at the last digit, decode that last digit by itself. So therefore, we're gonna preserve the tree here, but because this is not a valid branch, we don't even bother computing whatever this is at this branch location. So that's one observation. And now how do we decode W of 120? Well, by the same logic of how we deconstructed 1202, we have 2 options starting from the last digit of this subproblem. We can decode 0, or we can decode 20. The last 2 digits, because, right, we have 2-digit mappings and 1-digit mappings. If we decoded 0, that becomes the number of ways to decode 12. And if we decoded 20, that becomes the number of ways to decode 1. So the sum of these 2 ways should give the total number of ways to build the number of ways to permute 120. And again, we run into the same problem. If we decode the single digit of 0, well, 0, as we see in the mappings, it does not map to anything. So therefore, this is not a valid branch. So the number of ways to decode 120 is just going to be the number of ways to decode 1. And how many ways are there to decode 1? Well, it's obviously just one way, because if I only have the number 1, then that's just A, and I'm done. So the base case here is that the W of a single digit is going to be equal to 1, provided that this is between 1 and 9. Otherwise, it's just going to be 0, right? If the W of 0, obviously it's 0. So therefore, the number of ways is going to be 0, right, plus 1, plus W of 12. And we break down W12 in the same way we broke down W of 120. We can either decode the last digit, or we can decode the last 2 digits, which becomes W of 1 plus W of nothing. Now, this is obviously 1, and the W of nothing is going to be 1 as well. So therefore, 1 plus 1 plus 1 gives 3, which is our final answer. And that basically establishes how the DP works, right? The base cases are the single digit cases and the empty string cases. And then once we have those values, we can build up the solution with those base cases. And the recurrent solution is going to be that the W of I is going to be equal to the W of I minus 1 plus the W of I minus 2, which makes very obvious sense as we look at the tree diagram here, right? Because I is just going to be the very last element of the number. And the number of ways to compose the number up to the ith digit, 1202, right, is just going to be W of I minus 1 corresponding to the number excluding the last digit, and I minus 2, which is the number excluding the last 2 digits, which correspond to the choices we can make, either decode 1 digit or decode 2 digits. And once we have W of 0 to be 0, W of 0 to be 1, and by 0, I mean that up to the 0th index, so up to nothing, well, nothing is just going to be 1, as we saw in this base case, and W of one digit to be equal to 1, provided that the one digit we give it, and to be a bit more clear, w of n is equal to 1, where n is a single digit number and n is 1 to 9, right? We can build up the entire solution due to this recurrence formula. And we can now program this up in Python. All right, so let's program this up. So as we noted in the analysis, w of I is equal to w of I minus 1 plus w of I minus 2. And because to calculate w of I, we ever only need w of I minus 1 and I minus 2, we can just store these two values at any given time. Any other values will be redundant and it wouldn't be effective on the storage. So how do we approach this problem? Well, let's consider the case where the length of the string is 0. If n is equal to 0, obviously return 0, right? Because it means we have an empty string. There's no way to decode that. But we also have another case, and that's if the first element of the encoded string is 0. And why is that? Well, consider 0, 1, 2. There's no way to decode 0. There's no way to decode 0, 1. So because of that, there's no possible way to decode a number that starts with 0. And that's just an observation that you have to make. And from this, we know that, therefore, if we have a potential invalid message, then obviously capture that in this if statement as well. So hence we have this. And with that, we can move on, because if we passed this if statement, then we have a valid string that we can decode. So well, let's say we have 1 back. 1 back just means we decode the very last digit, and we want to consider how many ways are there to decode the number excluding the last digit. And since we have already considered the first digit of the number to be valid, let's start at the second digit. At the second digit, well, 1 back is going to be 1, because we know that s of 0 is not 0. So it has to be a valid number from 1 to 9, so obviously it has to have one case, one possible way to decode that one number. And 2 back is going to be 1 as well, because if we start at the second digit, then 2 back from that digit is going to be the empty string, and there's only one way to decode the empty string, which is one way. So now we can continue. For I in range of 1 to n, what can we do? Well, the current is going to store the next possible permute, right? The next possible way to decode the number, building the thing from bottom up. So if what? If the current digit, so int of s of I, right, is between 0 and 10 exclusively, then that's 1 to 9, so it's a valid number, then cur can plus equal 1 back. Because the second digit, if it's a valid one-digit number, then we can decode that, and it's a valid branch in the tree, so we can add the 1 back, because we can get to that previous case, right, as we saw in the example. And the same goes for the 2-digit case. If it's between the 2 digits, so I minus 1 to I plus 1, so this is a 2-digit number, it's less than or equal to 26, then we can decode the 2-digit number and then fall back to the 2 back case. So the cur has to plus equal 2 back. And once we have that, we now know the number of ways to decode the number up to the ith index. So how do we update these cur 1 back and 2 back values? Well, if we progress to the next iteration, what is going to be our 1 back? Well, our 1 back is going to be our current value, because we incremented I by 1. So 1 back from the next index relative to I is just going to be the current element right now, right? And then we also know that 2 back, right? Let's think about it. So once we increment, 2 back is going to be equal to 1 back, right? So we have to first do this, because 2 back is 1 back, because after we increment I by 1, the 2 back case is now the one that's immediately before it. And the 1 back case is going to be the current one, because we increment I by 1. So this makes sense. And once we're done, well, 1 back is always going to store the current number of ways to decode the value. So we have to return 1 back, which stores the number of ways to decode the string up to the ultimate nth index, the last index. So with that, it should work, which it does. So let's submit. And it works.